Okay, let's just see if something's on MathBreeze. Okay, so you have that multiple choice due tomorrow, and that's the last section that's on the test. The test is Monday. These sections 032 through 036, you have 046, sorry, you have the review online and the review videos as well. Okay, so we're going to go on with optimization. So here's a typical problem. This really is similar to one of the ones we did before, but it's phrased in terms of a word problem. Okay, so this one says, a farmer encloses a yard adjacent to a river. So here's the picture, like here's the river, and here's a yard. We should say a rectangular yard. Adjacent to a river. The yard must be 20,000 square feet in area. Find the dimensions that minimize the fencing used. Okay, so here's the picture. So if this side is X and this side is Y, this side would be X as well, and this side does not require a fence. That's the assumption because it's along the river. All right. Okay, so the perimeter, all right, that's what we want to minimize, is 2x plus y. So that's what you want to minimize. Minimize the fencing needed for that area. You could imagine that if you made the fence sort of very long, but still needed 20,000 square feet. I mean, sorry, if you made the yard very long or very wide, but still needed 20,000 square feet, you know, you would require a lot of fencing. You see all this, you would probably need a lot of fencing to get your 20,000 square feet. Okay, so it would, and if you made it too long in that direction or very long in the other direction, you would also need a lot of fencing. So it's somewhere in between. Okay. All right, so this is what we want to minimize. Now we're given that the area XY is 20,000. This is what we're given. So since we want to minimize this, what we want to do is we want to find dp, derivative of p with respect to some variable, okay, whatever variable, and set it equal to 0, either x or y. All right. So we first want to here this is x or y. We want to use this to substitute for x or y. So let's say we substitute for y. So y is 20,000 over x. So we'll substitute for y right there. Okay, so we have p is equal to 2x plus 20,000 over x. Okay. And now we're ready to differentiate dp dx. So differentiate, we have 2. And remember, the derivative of 1 over x is minus 1 over x squared. So here we have minus 20,000 over x squared. And since we're finding a minimum, we'll set equal to 0 and solve. Okay, so here's what we have. Okay, if we cross multiply, 2x squared is equal to 20,000. Or 2 is equal to 10,000. X squared is equal to 10,000. Or x is the square root. Okay, equal 1,000. So we get that x is equal to 1,000. Sorry, not 1,000. sorry, no, x is equal to 100. Let me, the square root of 10,000, so x is equal to 100. And we have that y is equal to 20,000 over x, so $20,000 over 100, so we have 200. So those are the dimensions, okay, that minimize. Actually, how do we know this doesn't maximize? Well, you can just sort of reason it out, really, because if you want to get 20,000, if you want to use a lot of fence, you can make this very, very, well, I think the better situation would be, this is the river, if you want to use a lot of fencing, have the fence go off in this direction. You can make it very narrow, and if you make it very narrow, it has to be very, very, very high. You can imagine, right? To get 20,000 square feet, you'd have to make this very, very, very high, and you would use an awful lot of fencing. So you definitely don't. So you're not maximizing. You must be minimizing. There is no maximum. You can reason it like that, but really, it's better to do a plus-minus analysis on dpdx. All right, there we have dpdx, so we might as well do that. We're going to put x equal to 100 there. Okay, 100. And 0, that's one place where it doesn't exist. For the plus-minus analysis, you put the zeros of the denominator, and you put the zeros of dpdx on the number line. So we're just making sure that we have a minimum. All right. Okay, put something in bigger than 100. Like, let's say we put in something like a million. Okay, then this is definitely going to be positive. This will be very small, and we'll get something positive here. Let's say if we substitute in 1, we have 2 minus 20,000, definitely negative. Okay, that's as far as we have to go. We just want to look to the left and right of 100. So here, negative, here, positive. We're getting, this is a min. Okay, that just confirms we have a min, not a max. Okay, this really is similar to a problem that we did yesterday, but yesterday it wasn't expressed as a word problem. Yesterday we just said the product of two numbers is something. Minimize. Let's say yesterday we had a problem like this. Let me just see. I think I have it here. The product of two numbers is 120. Minimize 4 times the first and 3 times the second. So that's similar to what we have here. Here we have the product of two numbers is 20,000. Here, let me show you. The product of two numbers is 20,000. Minimize 2 times the first plus 1 times the second. So it's that same exact type of problem, but expressed as in a setting, in this particular setting, this particular word problem. But it's the same type. All right, any questions about that? Okay, we'll do just a couple more. Let's look at this one. Here. So in this one we have a piece of a circle. Let's draw a piece of the circle of radius 5. This is a 5 here. X squared plus y squared equal 25. And we have some sort of rectangle, okay, inscribed inside. So we want to maximize the area. Maximize the area of the inscribed rectangle. All right, let's say this is the point xy. Okay, xy. All right, so the area is equal to x times y. Okay, and we want to eliminate a variable. Let's say can we eliminate y? So if we have two variables, before we take the derivative, we want to eliminate one. Well, so far we haven't used the circle at all. So if we just solve for y, we have y squared equal 25 minus x squared, or y is equal to the square root of 25 minus x squared. Okay. All right, so let's do that. So we could use this 25 minus x squared, and we have this. All right, so now we eliminated y. And now we're ready for the derivative, and we'll set it equal to 0. So let's take the derivative. dA dx. Product rule over here. First times the derivative of the second. Remember what the derivative of the square root is. I'm just going to remind you here. Another one that we should just remember. It's really a product. It's a simple power rule, but it's good to remember it because it comes up all the time. Okay, it's just a simple power rule. Exponent 1/2, bring it down. 1/2 x to the minus 1/2, and this is what we get. Okay, first times the derivative of the second. So I'm bringing down the square root, putting that 2 in, and chain rule derivative of the inside. So that's the first times the derivative of the second plus the derivative of the first. That's the derivative of x times the second. I'm going to write this over 1. I'm just going to add them so that it'll be easier for me to set this equal to 0. We'll just set the numerator equal to 0. Okay, so here we're going to add, those 2's will cancel, and so we have minus x squared over square root 25 minus x squared. Okay. And here we're multiplying top and bottom. We want that same denominator. Multiply top and bottom. Okay, so we'll do that. Okay, so we have plus 25 minus x squared, square root. And on the top here, the square root pops off. So we have 25 minus 2x squared when we add over that denominator. We're setting this equal to 0, so just set the numerator equal to 0 now. That's why we combined these two terms, so we could get a single fraction. And when we set it equal to 0, it simplifies to setting the numerator equal to 0. Okay, so that's what we were looking for, just this. All right, and so now we have 25 minus 2x squared equals 0. Okay, 2x squared equals 25. 25 over 2 equal x squared, and now plus minus square root. Okay, so we have 5 over square root 2. Now we're talking about, look where x is. X is in the first quadrant, you see, xy. So it's the positive one. So that's where x is, 5 over square root 2. And we can get y by just substituting into the circle. Okay, we'll just substitute in that. So we have 25 over 4. Okay. And subtract. So here we have 3 times 3/4 times 25. Oh, sorry, I see I made a mistake. Here, when we square this, we have a 2 in the denominator. That should be a 2. Okay, square this, we have 25 over 2. Okay. This squared, 25 over 2. Okay, so here we have 25 over 2, so here we have y squared equals 25 minus 25 over 2. Okay, so that's 25 over 2 for y squared. Okay, so y is equal to, just square root that, 5 over square root 2. So we see that x and y are the same, are equal. Right. Let's go back to the picture. X and y are equal. That means if x and y are equal, then it's along the line y equal x. This point is right along the line y equal x. X and y are equal. This is equal to this. So we have a square over here. A square will maximize the area. If it were not a square, if this were skinnier, the area would be less. Or if this were a little flatter, the area would be less. So that's what that tells us. Any questions? Okay. There are all kinds of problems. Like I said, we'll just look at a few different types. Here's, all right, I think I'll look at this one. This is a standard one that's done a lot. So let's look at this next one, number 3. I'm sure you have one like this on the homework. Let me check the homework. See if you have one like this. Yeah. Okay. This one's similar to the one of the homework problems. And here's the question. These optimization questions are very useful. Again, they're probably used a lot. They use a lot in real life. You want to maximize profits, for example, or there are situations where you want to maximize, volume. Like I mentioned, the suitcase problem. Maybe we'll do one like that, where if you're told by the airline that the dimensions should add up to a certain number, you want to make sure you buy a suitcase that maximizes the volume, given the fact that the sum of the dimensions has to be something in particular. So maybe we'll look at one like that. But first, let's do this one. This is also a practical problem. It says an open box is created by folding a piece. Here, I'll write down the problem. An open box is created by folding a piece of 12 by 12 cardboard with 4 equal squares cut from the corners. Okay. Find x, the side of one square. That maximizes the volume. Okay, so it would look like, the picture would look like this. You have a square, 12 by 12. Okay. So from here to here is 12. And from here to here is 12. And you're cutting out squares. So these are cut out. And then you fold along the dotted line. So the flaps, this flap, this one over here, and this one at the bottom. So those are the flaps of the boxes, will come straight out of the whiteboard, straight up, like out of the whiteboard. All right, and then you tape the edges together. So this is the X. These are all X's. Okay. So how do we represent the volume? I want a formula. We want to minimize the volume. Here we're only going to have one variable, X. We want to minimize the volume. But how do we represent the volume of the box? Okay, the volume is going to be this side times X. So the bottom of the box, this will be the bottom. This will be at the bottom edge, and this is the bottom edge. Okay, so what's this? That's the question. How long is that? Someone want to tell me? What's that length over there? You have the 12 here, so starting with that, what's this inside length going to be? Okay, so what is it? 12 minus what? Having to do with X. 12 minus what? You see, from here to here, we have X, we have 12, and we have X. So it's going to be 12 minus these two X's. 12 minus 2X, that's the inside. That's the edge of the bottom of the box. This is also 12 minus 2X. So the volume is going to be, well, the area of the bottom of the box, it's 12 minus 2X for one edge times 12 minus 2X. Multiplied by the height of the box, well, that'll be X. See the X coming out of the blackboard? When you fold along the dotted line, this measures how deep the box is. It's going from the bottom to the top. So X. That's the volume of the box. Okay, those are the 3 dimensions. When you get the volume of the box, you just multiply the 3 edges of the box. Okay, so that's our volume. And we're going to have to take the derivative. We should multiply through. Before we take the derivative, I think we can factor out a 2 from here and a 2 from here. Oops, I left out a 2 right here. 12 minus 2X. So let me put that back. Okay, so I want to factor out 2 from here and 2 from here. All right, so that would be a total of 4. So here I'd have 6 minus X, and here also 6 minus X. It'll just make it a little bit easier now to multiply. Okay, so now I want to take the derivative. I don't want to use the product rule. I just want to multiply everything out and get a sum of terms. So multiplying this out, minus X times minus X, that's going to be X squared. The middle term, minus 6X minus 6X, that's minus 12X. 6 times 6, that's plus 36. Okay. And I'll keep the 4 on the outside. Multiply through, we have X cubed minus 12X squared plus 36X. All right, now I have it in a good form for taking the derivative. There's no elimination here. We only had one variable. You can just keep that 4 there and start taking the derivative. 3x squared minus 24x plus 36. Okay. We can factor 3 out of this. We want to factor this, maybe first factor out a 3. 3 times 4 is 12. X squared minus 8x plus 12. 0. Okay. Let's try just see if this factors. Okay, so what do we have? 6 times 2, I think. X minus 6, x minus 2. That will work, right? Here we get plus 12, and the middle term is minus 6x minus 2x is minus 8x. So we get two solutions, x equals 6, x equals 2. Which one is it? One of these is the one that maximizes the volume. Which one do you think it is, 6 or 2? Which one makes sense? Okay, what do you think? Just by looking at the picture. All right, remember it's 12 inches top, right? Okay, it's 12 inches top to bottom. See, 12 inches top to bottom. Okay. If it were 6, that would minimize. 6 is actually a minimum. I'll show you why in a second. And this one's the max. So you're only going to cut out 2 inches here, 2 here. All right? So that's going to be the max. Cut out 2 inches. 2 inches. What happens if you cut out 6? 6 is, let me redraw the picture. The whole thing is 12. So if you cut out 6, you're cutting out the whole box, you see? You'd cut out that. You'd cut out this. This would all go, and you're left with nothing. You see what I mean? You're left with absolutely nothing. So that's why 6 is the minimum. Minimum, you minimize the volume. The volume is 0 if you cut out 6. So this one's the max. You can also do a little plus minus analysis, dv dx. It's right there. Put in 2, 6. Okay, right here. To the right of 6, we have everything positive. Okay, then if you put in 3, we have negative, positive, so negative. It's just going to alternate. If you put in 0, you have negative, negative, so that's positive. So I see here we have our max at 2 and our min at 6. Okay, so we want to maximize the volume, so x equals 2. So you see that's a real practical application of these max-min problems. All right, let's do one of those suitcase problems. Let's just think about that, because that's also a real life situation. Okay, let's say the airline says that sum of dimensions, sum of, let's say, luggage, because sometimes they go by dimensions rather than weight, or sometimes they have a combination. They go by weight, but they say also make sure the dimensions are, add up to a certain number. Sum of dimensions should be less than, let me just think what makes sense. I guess we'll do inches. I'm going to think about, I don't want to do something that doesn't make any sense, so let me do something that makes sense. I'm just thinking. Okay, so I'm going to do 90 inches. Okay. Okay, so let's say x plus y plus z should be less than 90, or let's say less than or equal to 90. So if the airline says that, then we're saying, let's say we want the largest suitcase possible. Okay, so let's say we need this equal to 90. X plus y plus z equal 90. And we want to maximize volume. That's what we really care about, is maximizing volume, because we want to take a lot on the airplane. So we definitely want to maximize our volume so we can take a lot of things, right? All right. We have 3 variables here, so I'm going to simplify the problem so that we only end up with 2 variables. Okay, so let's suppose, so we want to maximize the volume, and the volume is x, y, z. Okay, so now let's say suppose the suitcases always have z. Let's say z is the depth of the suitcase. Suppose z is equal to 20 inches. Let's say they always come like that. So now we're down to x and y. Okay. So the volume is equal to 20xy. Okay. Z is 20. And we have this little equation, x plus y. Just subtract 20 from both sides, x plus y is equal to 70. So we just simplified it a little bit. So we don't have 3 dimensions. So we don't have 3 variables to start with. We have 2, and we can eliminate 1. All right, so this is sort of a practical problem because the depth of most suitcases is about 20 inches. Most suitcases are, somewhat standard. So here, I'm assuming the suitcase looks like this. Let's say it's one of those stand-up suitcases. So let's say well, let me put x here and y here. And I'm assuming that the depth is 20. Okay, and we can have various x's and y's, so we want to know what size suitcase should we buy. Okay, all right, so let's eliminate a variable like we always do. Let's say we eliminate y. Okay, so y is equal to 70 minus x. Okay, so we'll put this in here. So first we do the elimination. Okay, so what's our volume? Multiply through, so we have 140, not 140, 1,402, 1400 x minus 20x squared. Now we're ready for dv dx. 1,400 minus 40x equals 0. Okay, so here's what we have. So just divide, and that tells us what one dimension should be. Okay, so I'm going to 140 divided by 4. Okay, so 35 inches. So x should be 35 inches. So that's what we should look for. Suitcase that's 35 inches, and y, we have y is 70 minus x. Okay. So y should also be 35 inches. So if you want to maximize your volume, you buy a square suitcase. That's what this says. XY, or buy one that's as close as a square as you can. Okay. The airlines sometimes give you these restrictions because they want to make sure that you don't take on things like something very long, like skis or something like that. That would be considered, maybe in some airlines would have you pay more for that. They want more standard size suitcases. Okay, so I'm just doing this example because it's a practical example. And there are a lot of practical examples, that use optimization. Okay. Let me just I'm looking at your homework. I want to do ones that are similar to the homework. So let me just look. I see there's one other one I have to do. Let me just look at the problems. Okay. All right. Okay, just one more to finish the problems that are similar to homework problems. So I want to do this one. Find the point on the curve y equals square root of x that is closest to 0.40. Okay, this will make sense when we draw a picture. Okay, so let's just draw a picture of y equals square root of x. So here, y equals square root of x, remember it looks like y equals x squared sort of on its side, just half of y equals x squared, half of a parabola on its side, like this. Okay, so that's what y equals square root of x looks like. Now let's look at the 0.40. This is 1, let's say 2, 3, 4. Okay, let me just continue this a little bit. Okay, so we want the point that's closest. Now, if we go straight up, if we were to go straight up, I don't think that's the closest line. If you were walking towards, if you were here and you wanted to walk towards like this curved wall and you wanted the shortest path, I don't think you would go like this. I think you would veer off a little bit towards this direction, right? I think this is better. That looks better. That looks a little shorter, right? Now, if you went a little this way, it's too far. So it's kind of near here, near this green dotted line, but a little bit to the left. That looks right to me in terms of shortest distance. But the question is, what is this point? That gives us the shortest distance. Okay. So we're going to use a distance formula. I'm going to call this, instead of d, this distance, I'm going to call q, because d is the symbol we use for derivative, so I'm going to use q. All right, so we need to use the distance formula. This point, let's call this point xy. Okay. All right, so we're talking about this distance that we want to minimize. All right, so it's equal to, I'm calling it q, just so I don't want to use d. So distance formula, subtract the x's, x minus 4 squared, and then subtract the y's, y minus 0 squared. Now we want to take the derivative. So first we want to eliminate a variable. Okay, this is a 0 here. Well, we haven't used the fact that y is equal to square root of x. So that's what we use here. Let's just use the fact that y equals square root of x. And that will be the elimination part. We'll get rid of y that way. Okay, this is a 0. Okay. All right, so here's the elimination. Q is equal to the square root x minus 4 squared. And then here we have square root of x squared. So we're going to get a fairly simple expression underneath that square root. Once we square everything out, maybe square this out, and we have x squared minus 4x minus 4x, that's minus 8x, minus 4 times minus 4 plus 16. And here I have plus x. You see? Square root of x squared, that's just x. So we have x squared minus 7x, just combine, plus 16. So that's q. Now we're ready. Now we're ready to differentiate. Okay? dq dx. Remember the derivative of square root of x, it's 1 over 2 square root of x. So here we'll put that square root in the denominator with a 2. But we have to do the chain rule, take the derivative of the inside. So here we have 2x minus 7 on top. All right, all we have to do, fraction equal to 0, set the numerator equal to 0. So just pull that out. So x equals 7 over 2. Let's see if that looks right. Back to our graph. What's 7 over 2? 7 over 2 is 3.5. It's right here. That looks like where we imagined x to be, right? We imagined it to be a little bit to the left. Sorry, not 3 over 5. 3.5. 3.5 I meant. 3.5. Let me erase that and write 3.5. Okay. It's 7 over 2, right? So 3.5. That's 3.5. That between right over here, half a unit to the left of 4. That's where we pictured it to be approximately. So that looks good. If we got something over here, we would know we probably made a mistake. It doesn't make sense. It has to look right. Okay. So that's x, and y is square root of that. X is that, and y equals square root of x. So that. So this is the point closest. That's that. Okay. Does anyone have any questions from the review sheet? Anything that you want to see? If you want to look at that, take a second to look at it, and you can ask me a question. Okay, all right. You have the videos, so you have everything worked out on the videos. I'll give you one more question. You can try this one on your own. Maybe you can try it at home, and we'll do it when we come after the test, when we meet next time after the test. So here's a nice problem to do, similar to this previous one. So maybe you should do this one on your own. Okay, and we'll finish it next time. Okay, so here's the question. You have, here's 0, and here we have the point 0, 2, and 1, 0. Connect these, and we have a line. This is the line y equal minus 2x plus 2. And you want to minimize this distance. Okay, I'll write this as 0, 0. Okay. Looks to me like the distance to the line should be around, the shortest distance to the line is about here. It's perpendicular to the line. Okay. So the question is, find xy. To minimize that distance. I'll call it Q. That's Q. Okay, so again, it's a distance formula, and you're going to substitute in. It's very similar to the previous one, so we'll leave that for next time. Okay, so do this. This is for after test for Tuesday. Okay, so I think we'll finish here. Study from the review sheet and the homeworks. That would be best. Do the review sheet, and then after that, first review sheet, then homeworks. Okay, and that would be plenty. All right. So enjoy your weekend. If you have any questions, you can send me an email, and I'll try to answer you. Okay, take care. Oh, wait, 1 second. Somebody asked to speak to me. Hold on. All right, I see. Ikra, you asked to talk to me. Sure. Go ahead. Ikra, are you there? Okay, you want to ask me a question? Right, did I give, oh no, I didn't, we didn't have the second test yet, right? So, right now, I had my other class, I already had the second test and I gave more time. I will be giving more time, like somewhere between, at most an hour and a half, something like that, okay? Maybe something like 15 questions, 15, maybe 16 questions. Usually I like to give 16 questions, something like that. Yeah, I'll try to make them shorter questions. So, I didn't make up the test yet. So depending on how long I think the questions are, okay, sure. hmm I'm not sure yet. If we finish early, then we could do it during class, on one of the scheduled classes, one or two of the scheduled classes. If not, then we'll do it during the final exam week. All right. So I'm not sure. It depends how quickly we finish. Uh-huh. Right. Okay, we'll see. When it gets a little closer, I'll be able to figure it out. So maybe ask me again. I'll see, how close we are to finishing the material. Hopefully we can do it early, but I would prefer doing it early, but I'm not sure if I'll be able to. Okay? So ask me when it, closer to Thanksgiving. Okay? Okay. You too. Okay, bye.